Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to go through, repair, and restore a really neat old Stewart Warner radio from around 1939 to 1940. So together, we're going to bring this old radio back to life again, make it receive just like it did way back in those years. Now usually, this older electronic gear has some form of a story to tell. It's usually seen quite a few hands between 1940 and now. So if there are any modifications or if there's anything strange in this radio, we'll talk about it and try and get an idea of what those people were thinking. And as we're going through this radio, we'll also get an idea of what the engineers were thinking when they designed this radio. We'll talk about that design as well. So let's get started. This is the really neat Stewart Warner radio that I picked up, and as you can see, it really is quite an unusual design. So it has a solid bakelite case, and there are no cracks, thankfully. They've mounted the speaker on top of the radio. Again, really kind of eye-catching. It kind of has that building kind of look to it. They've put some form of a wood grain finish on top of the bakelite itself, and as you can see, there's some form of checkering that's going on, so it might have some form of a clear coat on top of it. Now, this is a real fine line in restoration, and it really has to do with personal preference. There'd be a pretty easy way to get rid of that checkering. A little bit of work and some clear coat would probably take that away. And I really don't want to do that to this radio, just because I kind of want it to show its character from 1940. But I would like to settle off on that checkering effect. And there's a way to do it. And as you can see, I've kind of settled it off here, here, and here just by using some different chemicals. And basically what it all boils down to is just a wood preservative. So one of those spray-on wood preservatives on a rag. Of course, you're going to want to test this in an inconspicuous area. Basically, it's just a light oil. And what you do is you just rub that onto the finish, and it pretty much takes that checkering right away. Now, of course, it's not completely gone, and there are some scuffs and stuff in the case. Again, I kind of want that there because it does show, I guess you could call it the patina of the radio. It does give it an age. So again, personal preference. If you wanted to go through and restore the case on this radio and take all the nicks and scratches and everything, you could, spend some time with a bakelite in the finish. But for myself, what I'll do is I'll just use that preservative. Now, electrically, it's a different story. I want this thing to perform as good as new or better, and that's what we're going to achieve when we go through this. And that's what I'm going to share with you guys as we go through this entire radio here. We will make this radio perform like brand spanking new, because that really does show off the radio. It's one thing to have character in the case, but if the radio doesn't perform very well, that really takes away from everything. So we're going to spend lots of time in the resto and make this thing perform like it did when it rolled off the factory floor, and it might even perform just a little bit better because we're using some modern components in this thing. So as we come across these issues, we'll discuss what's going on within the radio and all the failure points, and we'll make this thing work like brand spanking new. So you can see the dial is working. It does get a little bit tight at one end. The keyboard's really nice and smooth. The latching action works really good, so the mechanical area in there is working fine. The switch seems to work, and the volume control doesn't feel too bad. Whether it works electrically at this point, I have no idea. Again, we'll encounter all of this when we go inside the radio. The little plastic bubble window seems to be in very nice condition, so a little bit of a polish to that. It should come out looking very nice. So all in all, we're off to a very good start. So what I'll do is I'll reposition the radio, and we'll take a look at the backside. So here's a look at the backside of the Stewart Warner radio. And at this point, what stories does this tell us? Well, there's actually quite a few just by glancing at this. First of all, we can see a bunch of screws here. So we know that by this little piece of cardboard here, the back of the radio has been ripped off at some particular point in time. I'm not really too concerned about having the back on the radio. So for originality, it is kind of nice to have it, but if it's missing, what are you going to do? Another thing I notice is the line cord. So this looks like the factory line cord down here. It's a brown rubber material. You can see that it's been black taped, and they've added a cloth cord to the rubberized cord, which tells me that this modification was done an extremely long time ago. So it has had some tinkering done to it. Another thing to look for in a radio like this is the antenna coil. Now, this radio has the antenna coil exposed. A lot of the times, these radios don't have that, but it is a real sore spot in these older receivers. Reason being is because these things usually were connected to some form of an external long wire. So I'll just shine a flashlight on the antenna coil. You can see the antenna coil right here. So usually these things are attached to some form of a wire outside the house or business, and of course if there's a lightning strike nearby, it turns that coil into a charcoal briquette, or at least opens the windings in it. So the coil looks like it's in very good condition, so that tells me that there hasn't been any lightning strikes or anything that's attacked this. Another thing that people used to do, which is really kind of odd back in the day, but you could probably way back when have gotten away with this, is they did a modification using some external components, and they tried to use the line itself, so the line cord and the plug in the wall as an antenna. Now, this is a very unsafe practice, and this really isn't something that should be done. But a lot of these radios suffered from burnt out antenna coils because people did that modification, and it just absolutely fries up the antenna coil. So another kind of strange thing that people tried to do back then. Now nowadays everything has a switch mode power supply in it, and even thinking of a modification like this nowadays is just completely out of the realm of even thought. It's just the line is so incredibly noisy. Some people even pass data over their line. So just definitely nothing that would work anymore in any way, shape, or form. And again, this is unsafe, so don't try to do this. Don't ever try to use the line as an actual antenna connection. So again, the antenna coil, it looks to be in good condition. So if there is something wrong with it, it is hiding pretty well at this point. So once we get into the actual restoration, we'll go in there and test that out. I noticed that the shields to the tubes are still in place. And you can see they have a socket here that won't really allow a metal tube to be plugged in there. So the modern replacements, or more modern replacements I should say, would have been a metal tube that would plug directly into this socket here. And this socket over here, like something like this tube right here. So chances are an actual glass 6SA7 would have been plugged into that socket there. Somebody's just put the more modern type tube there. Now those metal shields that you see on these tubes are known as GOAT shields, G-O-A-T. Now there are many variants of that shield, but it's just commonly known as a GOAT shield with a little kind of clip on here. So you take this clip, kind of like a retainer ring, off, and then the shield just splits into two. We'll take a look at those shields later and see if they have any writing on them or anything like that. The wiring to the speaker looks good. So this is the wiring that runs up to the speaker. This is an electromagnet speaker. So way back when, they didn't have permanent magnet speakers, so they had to put an electromagnet on it. And it also served as two functions. So not only would it magnetize the speaker, but it also acts as a filter for the power supply. So there's quite a few winds in this electromagnet here, and if the electromagnet speaker is missing in an older radio like this, you can perform a modification to get rid of the electromagnet, but it is nice to have that original speaker there. So if the speaker is unplugged, this is the plug for the speaker here, if it is unplugged, the radio will not function at all because the high voltage supply goes through that speaker. So at least through these winds here. The transformer that you see on the top of the speaker is the audio output transformer. So that's driven by this vacuum tube right here. That vacuum tube is a high impedance device. All vacuum tubes are pretty much high impedance devices. So the speaker itself is a low impedance device, so you need something to transform that, and that's what the transformer does. It transforms this high impedance device and allows it to drive a low impedance device. So whenever you're working on an audio amplifier or anything, say you've got a bunch of 6L6s or 6V6s or something like that, and it's driving a speaker, the vacuum tubes themselves are a high impedance device, high voltage high impedance device. And in order to furnish the drive power and the current to actually drive that speaker, you need to transform that impedance. And that's why vacuum tube audio amplifiers have transformers in the audio output section. Now, there are OTL, output transformerless styles and designs out there, but you'll notice that the OTL amplifiers use low mu triodes, and there's a lot of them to drive the speaker. So basically, what you're doing is you're taking a whole bunch of vacuum tubes and putting them in parallel to get the impedance down. And that's the reason that OTL style amplifiers have so many vacuum tubes. And of course they use low mu triodes because they have a lower plate impedance. Anyways, I'll get into that a little bit more in the future here. We'll start working on some vacuum tube audio amplifiers, and we'll actually design an OTL amplifier here in the future as well. Might even do that on the new bench. So these are the IF transformers. IF stands for intermediate frequency transformers, and when we take a look at the schematic, I'll explain the function of both of these transformers. This here is a dual gang capacitor here. So one of the gangs tunes the oscillator. The other section here will tune the antenna section. So that's a dual gang capacitor there. That's what does all of our tuning. Another thing to look for when you get a radio like this is you want to make sure that all the vacuum tubes are in place. Now, if you have a fair stock of vacuum tubes, not too big of a deal to go without them, as you just replace them. But vacuum tubes are getting a little bit pricey nowadays, and having the vacuum tubes there when you get the radio is kind of a nice bonus. Another thing that you're going to want to do when you get a radio like this is make sure all the vacuum tubes are in the correct sockets before ever applying any power to the thing. It's very common for rectifier tubes and audio output tubes to get swapped around. So this is the audio output tube. This is the rectifier tube. You can see the similarities, and you can see how they could very easily be interchanged. These are both ST style or shoulder type vacuum tubes. So whenever you hear ST style vacuum tube, that stands for shoulder type, or they're sometimes known as a Coke bottle. So just depends on who's using the terminology and everything at that point. So the speaker itself looks like it's in good condition. Doesn't look like there's any tears. I'll have to get the speaker out to see further. Something might be hiding in there, who knows. Again, when we service this chassis, the speaker will have to sit on the bench alongside the radio because the speaker is part of the circuit. Here we have a tone control, kind of an odd place to put a tone control, but it is on the back of the receiver, so they put that there. Here we have a phonograph input, so it says pickup, PU, and then there's ground here. So this can very easily be turned into something that can be driven by, say, a CD player, MP3 player, or even just directly from a computer. So if you want to play old-time radio broadcasts or just music through the thing, you can feed it directly into that point without having to actually use the receiver itself, and they sound really nice because technically you have a nice little tube amplifier driving the speaker up here. And so say, for example, say around Christmas time you wanted to play some Bing Crosby or something like that, it really does sound neat through these older receivers, and it does get a lot of attention as well. So actually they become the conversation point if you have a Christmas party. Everybody will be commenting on it. Been done many times here. So you'll notice that this radio has a power transformer, which means that this is not a series set. So most of the filaments in this receiver, aside from the actual rectifier tube itself, will be at 6 volts. Now, radios like this that do not have a transformer, so they don't have this big device right here, is most likely going to be some form of a series set, and they are dangerous to operate, especially if you want to attach something externally to them, because the chassis of the radio itself is attached to one side of the line cord. So you'll notice that way back in the day, the line cords were non-polarized. You see this one here? It's non-polar. Both of these are the same size, so you can plug it in the wall this way or plug it in this way, which a lot of the times makes the chassis hot. And that's a very dangerous situation. You'll notice that the radios that were series sets back in the day, they had all the knobs and everything are isolated from the chassis. So they didn't have metal knobs, and usually the chassis was shielded from the backside so you can't really touch it. So something to keep in mind. So the radios with the transformers like this are much safer than the series sets. If you're going to work on a series set, you need to have an isolation transformer, and there's a bit of a procedure to doing that as well. I've covered that in some of my other videos, and if we ever work on some series sets in the future again, I usually try and cover that in every video, just to be absolutely safe. Even when you're working on a radio like this, an isolation transformer is just a good thing. Reason being, there's little parts that hide in these things that leak. and cause problems. Now, some of these radios have bypass capacitors that run from the actual line cord to the chassis. And if those capacitors are leaky, and when I say leaky, I mean electrically leaky, sometimes they'll make the chassis hot. So there's some precautions that need to be taken place. So having an actual isolation transformer at the bench when you're working on things like this is a really good idea in all cases. It's just that one extra added step of protection. And when you're working on this stuff, you can never be too safe. So if you're used to working on solid state gear and things like that, vacuum tubes operate at high voltage. So there is quite a bit of voltage underneath this chassis and current supplied as well. So this is a high voltage rectifier here. So basically what it's going to take is the B+. Now the B+ is the high voltage. That's usually what it's known as on the schematics. This will put out high voltage AC. This will rectify it and turn it into DC, direct current, and then it'll get filtered by some capacitors that are hiding on the underside of the chassis. All vacuum tubes run at elevated plate voltages, and they also run at elevated screen voltages. There's high voltage all over underneath the chassis of these radios. That's just how vacuum tubes operate. In order to make electrons flow, they need to have a high voltage charge on the plate of the vacuum tube. So the plate of the vacuum tube is usually the outermost thing that you can see in the vacuum tube. You can see this kind of a dark area in the vacuum tube here. That is the plate, and that has usually a pretty high voltage positive charge on it, and sometimes there's quite a bit of current there as well. So things to keep in mind, if you're not used to working on vacuum tube equipment or radios like this, I strongly suggest that you look on schematics and do some reading up on vacuum tube radios and learn about the high voltage before you go probing around in something like this, because you can get a pretty lethal shock out of these things. So if you're following along, you're definitely doing so at your own risk. Please take care and definitely look out for high voltages and things like that. Always have that in your mind whenever you're working on a vacuum tube piece of gear. There is high voltage everywhere. In transmitters, high voltage is present on these caps. It's that exposed. It's like right there. So these are grid caps in this radio. These are receiving tubes, basically. They're not classified as transmitting tubes. So transmitting tubes have the plate connection on the top of the bulb, and the reason that they do that is because the plate voltage is so high that they don't want to run the plate connection down into the base of the vacuum tube. They want to have that cap on the top of the tube here. So the high voltage runs right into the top of the vacuum tube, so usually that's exposed. Another thing to keep in mind, so you need to know your vacuum tubes. So sometimes these are grid caps, which means the signal is going in here, and sometimes they are plate caps, which means the signal is coming out of here. So things to keep in mind whenever you're working on any type of vacuum tube gear. So there's a little bit of information there about this radio. I could keep going and going about the upper side of the chassis here. So what I'm going to do is remove the chassis and the speaker from the radio. We'll take a look at the underside and see what stories that has to tell. This is the bottom portion of the Stewart Warner chassis, and it's looking pretty clean. Doesn't look like a whole lot of tampering has happened over time. I can see a few things that have been changed, and we'll talk about those here in just a moment. But other than that, it's nice and clean. So it's always nice to get a radio like this, and that gives us something to go through slowly and basically methodically change everything and discover all the problems as we go, and that's what we're going to do. So you can see all the original paper and foil capacitors are in here. I see these two caps down here, they look a little bit different. They look like sealed tight capacitors, so these may have been changed. So they've pulled something like this out and replaced them with these. The original filter looks to be in here, and the reason I say it looks original is the solder connection to the chassis looks pretty clean, and it's done with a really hot iron. So you can see on the corner here, the solder is nice and clean. Usually when these things get replaced, techs don't have a hot enough iron, and you get solder joints that look like this down here on the chassis. Some pretty ugly stuff happening down there. Another indication that these have been changed, right? So it looks like they've added another filter capacitor over here, and the reason that I say it looks like they've added it is because they've got this horrible looking Y in here, and you can see it's very close to this connection right here. So, this could very easily short out. So somebody's tacked this in here. Now, right away, I kind of see what the old tech was thinking, and again, these things tell stories. So way back when, a lot of techs did not remove the old capacitor out of circuit. When the old capacitor failed, they just add a new one in. So they basically parallel in a new capacitor, which leaves a lot of problems behind, because eventually when these things really fail, sometimes they open up and then they short. So when these things really fail, i.e. short, what it's going to do is create a low resistance path to ground or to the chassis, and it's just going to ignore this capacitor. So whenever you replace capacitors, if you wanted to leave this in here just for looks, you'd have to clip the leads off of it and just basically leave the body in there. You never leave a faulty capacitor in circuit. Again, there's a high probability this thing will end up shorting over time. So I'm guessing that one of the sections in here opened up, and that's the reason that they've added this other capacitor here. And by now, who knows, maybe both the sections are opened up. All the original resistors look like they're still in here, so we'll have to check those and make sure that they are, reading correctly. Some of them drift quite a bit in value, some are okay. Now, depending on how many of them are bad, sometimes I'll just go in and swap all of them out. If most of them are pretty good, I'll just end up leaving them behind and replacing all the capacitors, let the radio run for a while, and usually if they've lasted this long, they're not going to fail with new capacitors. Very rarely do they. Sometimes they will get noisy, things like that. Again, it's up to the person that's going to be restoring the radio. If you want to spend the time and replace every single resistor, that's absolutely fine as well. Just whatever you're into. So what else here? The line cord, nice and soft still, but where it's entering the back side of the radio, look at that, it's completely bare. So if you're to plug this line cord in, there'd be a nice big flash. So definitely pretty bad there. Don't want to be using this. So what I'll end up doing is I'll just clip this thing out. Now, what I'm going to do is I'm just going to put a line cord onto this thing, and I'm going to bring it up very slowly on a current limited supply that has some, basically like a dim bulb tester. There's also an isolation transformer there as well. So it's a variac isolation transformer and dim bulb. So basically a current limited supply. What I'm going to do is bring it up slowly, and we'll try and find where all the problems have kind of occurred here over time. So there may actually be, short circuits in here, or there may be open connections. So what we're going to do is just trace out all the issues. And then, of course, we're going to replace all the components. But it's kind of neat to see what the actual failure point in this radio was. So basically, why did they shelf this thing? So this thing went and sat on the shelf because, say, for example, this resistor here opened up and it didn't make sound anymore or something like that. So it's usually one really big issue that stops these things from working. But, again, because all of these capacitors are degrading over time, it's just going to be a slow decline into a very silent receiver, right? So this is an air core oscillator coil right here. So these are the adjustments for that coil. Looks like, yeah, they're running to that oscillator there. There's some more alignment points up here. All of these variable capacitors here are for the push buttons on the front, so you can program those push buttons. See the push buttons move in and out here. So that's what these are all for, and they all look to be in pretty nice condition too. You can see that there's not a whole lot of marring on the actual little screw head here, so nobody stripped them or over tightened them. I don't see any cracked ceramic or anything like that. So all in all, it looks pretty decent. However, this was a little bit disappointing. Look at the speaker. So again, I can see what's happened here. So this doesn't look like it's, been out all that many times. This thing doesn't look like it's been out of the chassis. Maximum, I would say 3 times, possibly, for this cap, maybe that sealed tight and that sealed tight over time. I would imagine since they're both the same, they replaced both these caps at the same time and then added this one. So it may have been out of the chassis twice, something like that. Now, what ends up happening is because this speaker is part of the circuit, it usually sits on the bench beside the radio like this, and it has to be plugged into the back socket over here. So what happens is somebody's got a screwdriver and they drop their screwdriver, or, or their roll of solder or something ends up falling on the speaker and doing this. And this is, very common. Now, luckily, the speaker looks like it's in pretty good condition. If I move the voice coil, there is no binding whatsoever. It's nice and clear. So there's a good chance that this can be resurrected. So what I'll end up doing here is I'll just get my tuning tool and I'll pop this under the paper here carefully. If I can get it under there. You see, I'll just lift the paper back up like this, and just glue the paper right over here. So lift that up, and it should be okay. You know, maybe fix this little crack over here as well. You don't want to leave the paper like this. So this is really common. So a really good idea to keep these speakers safe when you're working on a radio like this is put them face down and then put a cover over top of it. So just put something on top. So if you drop a screwdriver off to the side or you bump something, it doesn't go through the paper. When you test the radio out, you want to make sure that the speaker is clear, just in case you know there's any kind of arcing and sparking on here, because there's high voltage running through this a lot of the time. Now, in some cases, the field coil is on the low side. It's in the center tap line. It just depends on the radio's design. But we have an audio transformer here that will definitely have high voltage across it. So we'll take a look at the speaker here more in depth in just a moment when we take a look at the schematic. So just a few ideas to save the speaker. It's more often than not, you find those speakers in older radios like this, and they're just, I've seen some of the papers completely missing. So that's disappointing that you have to completely replace the speaker. And there's not a whole lot of room in here where I'd want to add some form of a large resistor, you know, to replace the field coil. Could be done, you know, find a chunk of chassis maybe over here, put a large resistor over here and, you know, screw it to the side of the chassis, something to replace it, and just put a permanent magnet speaker in there. But then you still have the issue of you know, the actual audio output transformer. You'd have to find a place for that as well. So it's always nice to keep things original and looking original on the outside. So I'm not too worried about, you know, modern components on the underside of the chassis here, because it's not seen, and of course you want the radio to perform properly, right? I managed to find a pretty nice looking schematic for this radio. So this is the schematic for the Stewart Warner. Nice and clean, alignment procedure on the bottom. Couldn't ask for anything nicer than this. So this tube here, the 6SA7, is a mixer and oscillator. This tube here performs two functions. This is the first IF transformer. So this would be this transformer right here, the first IF. This is the first IF amplifier tube, the 6K7G, which would be this tube right here. So you can see G stands for glass. That's the reason it has those shields on it. This is the second IF transformer here, which would be this transformer right here. This goes into this tube here, which does a bunch of functions as well. So this has got a bunch of diodes and a triode inside it. So this is a detector tube and an audio amplifier tube. And that's this tube right here. The 6F6 right here is the audio output tube, and that's what drives the speaker. So we can see connected to the transformer and the speaker over here. That's this tube over here. This is the rectifier tube, 5Y4G over here. That's this tube right in the front. That's a high voltage rectifier. This is known as a full wave rectifier. So you can see a center tap running here through the speaker field down through a resistor divider to ground. So they've actually got the speaker field in the negative line here, which is kind of nice because it keeps high voltage off of this. So, you know, less chance of breakdown and things like that. It's kind of nice that they did that. You'll notice that this tube here has its own dedicated filament winding. So this one winding here is only for this vacuum tube. Reason being is the 5Y4G is a directly heated vacuum tube. That means that the cathode and the filaments are the same thing. So what's going to happen here is, because we have a full wave setup happening here, we're going to have high voltage on this filament winding. You can see that it's attached. The filaments are directly attached to this winding. We wouldn't want to have this winding, you know, powering the filaments of all the rest of the vacuum tubes, because then we'd have, you know, high voltage on all the filaments, and then we risk a problem called filament to cathode breakdown. So we wouldn't want to have that happening. So this gets its own dedicated filament winding, and it's a 5-volt winding. You can see 5 is the first number in the tube, the actual the tube identification here. So 5 means the filament voltage. So, full wave rectifier, we have DC at this point here. We have an 8 microfarad capacitor going to be doing the filtering here. We have a bunch of 8 mic capacitors here, one here, here, and here. And of course, this is our B plus line. You can see that it's going to the screen grid and through the transformer to the plates of most of all the tubes over here. We have a power transformer here. There's no AC bypass capacitors on this side, which is kind of nice because it eliminates a problem. You know, if those capacitors leak, you know, there's a chance of it making the chassis hot, right? So there's none of that here. So we have a shielded transformer, this dotted line here, and this little ground symbol means that they're using a shield in the transformer. Kind of nice. These here are all the selector switches for all the programs and everything here. And we can see that, everything is listed here, all of our adjustment points, C4, C5. You can see here C4, C5, and then we see C6, and C7, C8. So it's kind of nice they've got the alignment procedure on this paper and everything. So when we go through and do the alignment procedure, we'll follow this and align the radio up, and I'll show you how to do that exactly. Here we have the volume control over here. This is the phono pickup. So if we wanted to modify this, probably have to look into this and maybe change some values to modify this little area here if you wanted to use a CD player, MP3 player, or your computer or something like that. I'm not sure if there is any type of capacitors in line here. It would be just safe to put a capacitor in line with this as well. So create a DC block between your device. And if you're going to use a headphone jack or something on your computer, it would also be good to terminate this to ground with an appropriate impedance. Say, for example, a 16 ohm headphones or something like that. You'd want a 16 ohm resistor here to ground and then a blocking capacitor. So we might cover that later, depending on if we modify this for a CD player. It just depends on how far this video goes. Tone control. This is that switch on the back side of the chassis here. So it looks like a 0.004 microfarad capacitor. That'd be 4,000 picofarad if you want to look at it like that. So basically, this is just attached right to the plate of the 6F6, so kind of a brute force tone control. Just clamp it down with capacitance. So that close that switch there, and I guess it gets rid of the highs. So probably for staticky situations or, really tinny audio, something like that. So brute force method right there. Let's see, what else do we have here? Just the standard coupling caps. There's 0.1. We have a 0.1 on the line here to keep RF off this long line here. So you can see that we have an 8 mic on this end over here, which is acting as filtering, and then way down here we have a 0.1. So again, just keeping RF off the line here because we don't want any RF moving from stage to stage, or we get oscillations. The radio will howl and things like that. So the placement of these capacitors is really crucial within the circuit here, and of course this is where the engineers were thinking when they were designing this thing. Depending on their layout on the chassis, like how they've laid the tubes out here, a lot of the times this is just trial and error. So, the engineers are like, we got howl, so we're going to, if we put a capacitor right at this IF transformer and a capacitor right at this IF transformer, it should get rid of that, and stop any RF from traveling and getting any kinds of oscillations and things like that, right? So, all in all, it's a nice clean schematic, pretty easy to follow. So we'll revisit the schematic as well as we're going through the bottom side of the chassis here and, doing some troubleshooting. So I'll point out parts and pieces and things like that as well. Just before I go applying AC to this Stewart Warner radio, I want to make sure that there's no dead shorts or anything dramatic happening inside this radio. Also still have to get rid of this line cord here, so don't want to apply any kind of AC to this until all of this stuff is out of here. So it's always a good idea just to check, make sure there's no, bad shorts in the B+ line or anything like that. I don't want to damage the rectifier tube or anything like that. Now again, I'm going to have a current limited supply, supplying the AC to this thing, but why not just test and make it that much safer, right? No point in trying to harm anything. So in order to verify the components inside this chassis, I'm going to use a thing called a signature tracer. Now, this is one of the scopes that you saw in the earlier video. This is the WO33A oscilloscope, but this has been converted into a curve tracer and a signature tracer. So by using this, I can very quickly verify the components in the chassis without having to remove them. So what I'm going to do is just ground the curve tracer, signature tracer to the chassis here. And I'm going to check out this capacitor. Now, if you recall, we have the black lead that goes directly to the chassis. That's the reason I'm using the ground to the curve tracer, or common if you'd like to call it that, to the curve tracer here. So the first capacitor that I'm going to look at is this green lead here. So what I see here is just pure resistance at this point. If there was any capacitance there, I would see kind of what would look like a tilted circle with that resistance. So I'm guessing that the capacitor in this is most likely open, and I'm seeing this resistor down here, which is part of that divider that we looked at earlier. So it's on the other side of the field coil, and this speaker plugs into here, and this is the field coil that attaches right to this terminal here. So what I'm seeing is just pure resistance, and that would most likely be this resistor down here. Now there's another resistor here, but this is a very high value. Now when you're reading these old resistors like this, you have to just remember bed, like the thing you sleep in. Body, end, dot is what you want to remember. That's the order that you read it. So the body is this part here. So the most of this that you see, which is the brown, so that's going to be 1, end, which is black, which is 0. So, and then we have the dot, or the stripe in this case, which is green. So we have 5, so 105, which is telling us this is a 1 meg resistor right here. So again, if we wanted to read this large resistor here, so it's body, end, dot. So body, end, dot. So this is 6, blue is 6, gray is 8, and we have red, which is 0, 0, or 2. So we have 6, 8, 2. Now the last one, you can always take that number and turn it into zeros. So this would be 6, 8, and then 2 zeros, 0, 0. So 6,800 ohms is this resistor right here. And that's how these all read. So the value of this resistor down here is pretty low. It's, I see red, so 2, and then black, end, 0, and then 1, which is brown. So this is 200 ohms right here. So 2, and then 0, and then 1, which would be 1, 0. So that's the reason that I'm seeing this resistance. This is seeing that 200 ohms right there when you're looking at the screen over here. Again, if this was showing a capacitor in there, it would look like a sideways kind of circle. So let's take a look at this red lead right here on this capacitor. And that's basically what I was just trying to explain right there. So we have a sideways circle. So I'm seeing resistance in with capacitance. Now, if this capacitor was working and it was working okay, it would be a straight up and down line with a small little gap in the center. The capacitor that I'm looking at here would be very close. I would say somewhere between 0.01 and 0.1 microfarad. So, and that's just due to the test frequency that this little signature tracer is at. So what that's telling me is this is looking at a capacitor. Either this is almost open and it's turned into a capacitor around 0.01 to 0.1 microfarad, or you can see this lead runs off down here to this junction point, and there's another capacitor tied to that junction point to ground, and this one is 0.1 microfarad. So you see we get the same reading if I go down here, or if I go up here. This is just connected by this wire. So what I'm thinking is this capacitor is most likely open, just because we don't see anything here. We just see that line. There's no circle or anything in there. It should be straight up and down. And this here is kind of a sideways circle, which is indicating resistance. So resistance is indicated by sideways, and the circle is indicating capacitance. So not a whole lot of capacitance there. Now, since this, you can see, if you look at the angle of the circle here, all right, and you compare that angle to what we see here, all right, the angle is a little bit more straight up, all right? So that means that this down here is a higher value. Whereas if we look at this, you can see it's on a little bit more of an angle, so it's a little bit closer to being open. Now, what this is telling me is chances are, because of the angle here, it's in the ohms somewhere. What that's telling me is if this is the capacitor that's leaking, it's turning into a short. It's probably, below 1 kilo ohm somewhere. And this is probably going to end up shorting the B plus line, is what I'm gathering. It'll be either this or this, if this one is turning into that short. So these are the two culprits right now. So I would be very leery about trying to apply any kind of AC line to this right now, because I might damage something. So let's take a look if this capacitor here is okay. It has a separate ground. So I'll just apply this to here, and I have to get down to the bottom side of that tube socket. Its other connection's way down in there. Hopefully I can get at it from here. There we go. Okay, so that's looking like a capacitor. I don't know if you can see the gap in the two lines there. There's a very slight gap. Again, that would be more pronounced if this had a different operating frequency. So this is operating around 1 kilohertz. So I don't know if the camera's going to show that up. I'll take a look in the viewfinder here. No, it's looking like a straight up and down line, but there is a gap in there, a very slight gap. So that's telling me that this capacitor is most likely working okay. Good reason why they probably replaced this and shoved this thing in here. Chances are this gave up and they tried to patch it with this. So as you can see, the story's kind of coming together. You can kind of see what the tech was doing. So let's take a look at some other capacitors. So this is right to ground, so we saw that by looking at this. So let's take a look at this capacitor here. So if this is, let's take a look at it here first. So that's how it should look. Now there's a very slight tilt to the circle, which is indicating leakage. And you don't need to be any kind of a rocket scientist to know that all of these wax capacitors are leaking in some way, shape, or form, and they have some form of resistance. But you can see that that's more of what it's supposed to look like. All right, so when we go to this point here, if we were just to look at this capacitor here, it should look like that. But you can see we do have resistance there. Resistance indicated by the sideways motion of the sideways tilt here. Now, the B plus line in this thing virtually should look open, or very close to being open, high in the k ohms at any rate, because the B plus line in this thing is just attached to the plate circuits and the screen grids all the way along. So, of course, it's going to find resistance paths to ground, and things like that along the way, but nothing like this. This is very pronounced. So this is definitely showing me that there's an issue. What I'm going to do to verify this is go and get an ohm meter here in a moment, and we'll hook an ohm meter across this and just check it out and get an actual ohm reading. I'm gathering this is probably below 1 k ohm, which is, looks really nasty to the B plus section. So let's take a look at another cap here. Let's see this one down here. This also runs to the chassis, and it runs up here, I think. There we go, looking okay. And there's another one here. We have this one that runs from here. Here, let's see. No, that's not grounded at that end. I don't know where this is running off to. It looks like it might be going onto the top side of the chassis. So let's go from here. It's going to the volume control here. So no problems there. Yeah, let's see. Now when I'm saying no problems, I mean that the radio would operate with that cap. It's not saying that it isn't leaky or anything like that. So this one goes way off somewhere and hides. So let's take a look at this one here, this solar. It goes right down here. You can see the negative of the foil end side attaches to the chassis, so we'll go here. And that's looking okay. So nothing would happen with that capacitor there. So this is a mica here. I imagine this is probably okay. Yeah, no problems. I don't know if you can see that line part there. So that's okay. No problems with that mica there. Now, if you were to picture this straight up and down on this end here, when I looked at this capacitor down here, it looked like that straight up and down. I just don't know. It was a little bit tighter than that, so you can see that gap in the line there. So again, this capacitor looked like that straight up and down. Right, so this is getting higher up in the microfarad region. I don't know what this is. It looks like it might be a little bigger than 8 mics on the screen here. We'll have to turn the body around and find out what they've put in here. This is a patch job, right? Somebody put this in here to try and fix this. So yeah, well, you can kind of see what's going on here, right? This thing is bad, so they want to get rid of the hum, so they, put in some, a larger capacitor of some sort. I imagine it's probably higher than 8. So 8 is a pretty low value. Let's see what else. I think that's, we're getting pretty close to getting an idea of what's going on. Let's see this here. Yeah. So what we know so far is chances are we have a problem in the B plus section. So I'll just go get an ohm meter. I'll be right back and we'll take a look and see if what we see here is correct. Okay, so let's verify this. So what I'm going to do is take the negative probe and again attach it to the chassis here. We'll take a look at this B plus line and we'll see what we get. 647 ohms. So 0.647 k ohms is 648 ohms. So if I was to apply power to this thing, so if I was to attach the AC line to this thing, I would probably damage the rectifier tube, and I definitely wouldn't want to do that. So, as you can see how quickly that curve tracer verified that. So, it'd be interesting to take a look at the capacitors and see if these are actually open. And in a moment here, what I'll do is I'll just clip the leads off. It's going to have to come out anyways. So, I'll just clip these open and we'll check this capacitor here. So, may as well just do that right now. Let's open this lead up and open this lead up. So see what we have. So we'll go to capacitance here. All right, and put this back in the chassis just to find a nice little place. And let's try this here. 28 nanofarad. It's open. Let's take a look at this green one here. 14 nanofarad. This thing is completely open. Now the interesting part, now that this is unhooked, this will really tell us if this capacitor here is at fault. So I'll just move that out of the way. And we'll just take a look at this here real quick. Yeah, I'm thinking that this here capacitor is the one at fault. So when we looked at the schematic, if you recall, we saw only 1.1 microfarad capacitor on that B plus line, and that would be it. This is the junction right down here. Everything seems to join at this part. It's kind of like a, I don't know, looks like a cobweb of wires coming to this one connection right here. You can see all of these wires and resistors and everything off to this point. So I'm imagining that this wax capacitor here is the culprit. So what I'm going to do is just go get a soldering iron and I'll heat this joint up and pull this capacitor out, and we'll see if this is the culprit. I'll be right back. Okay, my soldering iron is now on this bench and it's heated up, so see if we can get this in here. Came out of there, kind of nice. All right. So let's take a look at that B plus line again, now that this capacitor is out of here. Very slight resistance and a little bit of capacitance there. It's looking a lot better. Let's take a look at this capacitor. Get a connection on the end here. There it is. All right, so let's measure the resistance of that. So this guy's looking like the culprit right here. Let's move this out of the way. Grab the other meter here again. It's going to be a little bit defocused because it's in front of the scope there, but you get the idea. So just attach this to the chassis here again. We'll take a look at this. And this capacitor right now is reading 1.5 k ohms. So chances are it's moved up a little bit. Let's take a look at this connection here. 53 k ohms, right? So this is almost looking open to that circuit now. So it's way up there. No problems here now. So this capacitor here should look like an open circuit. And it's measuring 1.6 k ohms right now. So this is an incredibly leaky capacitor. So chances are this thing would get hot and start festering, and chances are it might even pop, blow the end out of it or blow wax out of it if we were to plug this thing in. You can see it's slowly moving up, and that's because I've heated this lead now and I've pulled this out. So I put a bit of stress on this. There it is. Move it around a little bit. So just putting any kind of stress on this is going to change the value. So if you ever want to find a component like this, it does get a little bit tricky. You got to remember these are wax capacitors, and any kind of heat on this lead is going to affect this, right? So because the wax is soft and you heat it, and it's going to change value just a little bit. So this capacitor is definitely shot. So that one's rated at 0.1 microfarad. What I'll do is I'll just go grab one right here. So this is a newer 0.1 microfarad capacitor right here. So what I'll do is I'll just put this on the bench down here. Try and get that in the shot. I don't know if I can. So I'll just touch the leads of the signature tracer across this, and you'll see a nice pattern on the screen. There you go. It's not looking leaky at all. So that's how 0.1 should look, and you can see here, because of the angle with this, we can tell it's leaking. So not only can we tell that it's acting as a capacitor, but it's acting as a leaky capacitor, all with one reading. That right there. Circle's looking kind of ugly as well. So now that the B plus line is freed up, I might actually be able to plug this thing in. So what I'm going to do is I'll clip the line cord off right now, and we'll take a look at the transformer. So I'll just poke this across here, and I'm getting nothing, so that means that the switch is off. Let's turn the switch on. There we go. Yep, no problems. Transformer is okay. So everything is looking good so far. Again, this is still in line, and we're seeing 53K or something like that, as you can see here. And we're still going to view some capacitance in here, right? Because this is still linked up through this whole system, and there's a very slight tilt there, so a little bit of resistance. 53K is not going to be too much of an issue to worry about. So what I'll do is reposition everything here, and we'll try this out. Actually, you know what? Let's test the speaker first. That would be a better idea to do that. So let's check that out. All right, let's test out the Stewart Warner speaker and associated circuitry here. See if this thing works. Ignore the blue coil on the underside here. That's just suspending the speaker into the center of the shot. So the coil form happened to be the perfect diameter of this speaker here. So it's just sitting on top of that. Boy, you can really see the tear in the paper here. I'm going to definitely have to fix that up. Anyways, this here is the audio output transformer. So the 6F6 audio output tube is driving this transformer, and this transformer drives the voice coil of the speaker. Again, vacuum tubes are high impedance devices, and in order to get any sound out of this speaker, or at least a comfortable level, we need to transform that impedance. So that's what this thing is doing. It's taking a high impedance device and transforming it down so that we can drive the voice coil of this speaker here. So this here is known as the field coil, this large area right here. Now, the field coil's job is basically to act as a filter in the power supply, and it also magnetizes the speaker. So basically magnetizing this pole in the center here. Now, the field coil itself is in the center tap line of the high voltage in this particular schematic, and then of course that's finding its path down to chassis ground. Now, since this is in the center tap, this is going to be acting as a filter, so there's going to be some hum present there, right? And that hum can show up in the actual speaker itself. So in order to try to cancel that hum out, what they've done is they've added another coil on the top here, somewhat of a pancake-style coil. This is called a humbucking coil. So what they're doing is they're basically using this, and I guess you could call it, they're using this to sample or listen to this coil here, and this coil is 180 degrees out of phase. So this coil is in series with the output winding of this transformer here, and they're feeding a 180 degrees signal out of phase trying to cancel any hum that's coming from this coil. And that's the reason that the humbucking coil is usually sandwiched right at the backside here on top of the field coil here. So whenever you see this coil here, the humbucking coil will measure at a very, very low resistance if you use an ohm meter, right? It's a very low impedance, low impedance coil, very close to the impedance of this transformer's output winding here. So you can see this is in series but out of phase with the winding here. So if you look, you can see that this black lead that goes into the humbucking coil goes into one end. And then you can see the one lead from the audio output transformer runs into here. So you can see that one lead goes into this yellow lead, goes through the humbucking coil and down to the speaker's voice coil. And on the other side, you'll notice that the output winding here just goes directly to the voice coil. So the humbucking coil is in series, and that's how you can tell that that's a humbucking coil. Now, humbucking coils, again, if you want to test it with an ohm meter, it'll read an extremely low resistance. So extremely low resistance on the curve tracer here looks like straight up and down. So basically what I'll do is, and of course that's in series with the secondary winding here or the output winding of the transformer. So this is going to look like a dead short, a straight up and down line if I touch this here and here. You can see that. So it just looks like a dead short. Now, even with this curve tracer and signature tracer, even just going across the humbucking winding like this, you can actually hear an audible tone in this speaker, even though the actual field coil is not energized. So it's kind of a nice test. Now, the signature tracer, in order to test things, has to put a signal out the leads. All right, so there's a signal coming out of the leads, and then it puts a signal across the device, and then you get the result on the screen here. That's how this thing works. So we can use that signal. When I designed this thing, and I designed the circuit board for this, I designed a very, very low distortion oscillator in here, so it can actually be used to test audio amplifiers. So if you need a low distortion signal to test an audio amp, this thing will provide it, very low distortion. All of the plans and everything to build this are on Patreon. So all the printed circuit board layouts are there, all the parts and everything that you need to put one of these things together, and complete instructions on how to fit it into an older $5 or $10 oscilloscope and make it a very effective piece of test gear. So check that out if you're interested in this. So I'm just using this to test this because it's a very easy way to test this out. So if we want to very quickly test the audio output transformer and see if the voice coil is working, all we want to do is locate the two leads that run to the plate and B plus of the 6F6, and that's these two leads that run right into the transformer. Again, this provides enough drive that we don't even need to energize the actual field coil in order for the speaker to make sound. So what we want to do is find these two leads in the socket right here, and that's these two leads right here. So what I'm going to do is just put the curve tracer across these two leads, and if you listen carefully, you can hear it working. So that's actually working very well. So again, keep in mind that this isn't even magnetized, and it's making a signal. So everything is working there. So we know that the audio output transformer is working. We know that the humbucking coil is not open. We tested that here. And we know that the signal is getting through the humbucking coil and the voice coil is working, all with this simple test using the tone from this device. If we want to test the field coil, in order to see inductance, we're going to notice kind of an oval and it'll be on a tilt. All right. So if we want to see if the actual field coil is working here, I'll just attach to the field coil. So the field coil is these kind of striped lines here. You can see the striped lines go directly into the field coil. So in order to test that, all we do is just clip this here and look at the result on the screen. There it is. And you can see that we have that little oval there, the part of the lines, and there's a slight tilt. So you can see that. I'll just touch it here. So we know it's acting like an inductor, and it's working. So now on the schematic, if you want to test the field coil a different way, a lot of the times, and sometimes not, they include the actual DC resistance. So I'll just just move this out of the way a little bit here. So you can see here, they actually write the DC resistance here, 1400 ohms. So if you wanted to test that with an ohm meter, it should be close to 1400 ohms. Now, usually they're not spot on, something, maybe 1450 or something around there. So as long as it's, 1380 to 1500 ohms, you'll probably be fine. So again, usually it's not right spot on. So what I'll do is I'll just grab my ohm meter here and let's just test it, see what it comes out as. Another good way to also see if the speaker's actually been substituted with something else. Okay, so I'll just make a connection across these two right here. So I'm going to have to clean these off. They're actually very dirty connections here, so hopefully I can get a decent reading here. Let's see. Here we go. Yeah, so 1.48. So 1.48K, so almost 1.5. So 1.48, that's close enough. So we know that the DC resistance of that field coil winding is pretty close. And that's really standard when you're testing devices like this. You're usually not spot on. So there you go. And that is how you test the field coil winding, the audio output transformer, and the voice coil, and the humbucking coil very quickly on a speaker like this. Just for the fun of it, let's see if the radio comes to life in the current state it's in. So the current state it's in means that this capacitor is completely disconnected. Not as if it did anything anyways, it's completely open. So that's out of circuit. And our capacitor that looks like a short circuit to the B+ is unhooked, and we'll verify that here in a little bit. I'll use my my current limited supply, and I'll put this capacitor in circuit, and we'll see what happens to the high voltage. So we want to try this thing out, so the first thing we should do is hook up the antenna. So let's do that. This looks like the darker of the two leads, so that should be chassis ground. I'm hoping that's chassis ground. If it isn't, not a big deal. Okay, it just won't receive. That's not too big of a deal if it isn't. I'm thinking it is. It's the darker of the two leads. Okay, so that's out of the way. Let's hook up the isolation transformer and variac supply. So attach this to where the line cord normally goes. These two lines are open here, so that was attached to our line cord, which is very badly shorted at this point, so that's all completely cut out of circuit. In fact, I should probably just cut that right off, take that out. Yeah, do that later. Okay, so let's attach the voltmeter across the high voltage. So one lead goes to ground, other lead goes to B+ line here. And I'll turn this on, so we'll see what we get. Okay, so now I'll move the camera over to the isolation transformer and variac supply up here on the wall. So the variac is halfway up. We'll start with that right down. This is in current limit and it's off. So what I'll do is I'll turn this on and we'll bring it up to about, we'll say 60 volts or something like that first. We should start to see just somewhat of a dim glow in the bulbs on the top. Just starting to glow. Don't know if the camera's picking that up. And if we look at the high voltage down here, we can see that it's coming up. And when the cathodes start to warm up in the tubes, it should probably settle off and start to go down because the tubes start to draw current. And it's doing just that. This radio is pretty predictable, isn't it? Okay, so now what I'm going to do is we'll take a look at the supply up here again. So what I'm going to do is advance the variac. Bring it up to 100 volts, and we should start to see the bulbs glow a little bit more. Now, that's not glowing very bright at all, so that means that there's no issues. So that's looking good, and it'll get just a little bit brighter as I bring this up to the top. And I would say that that's quite comfortable. So there's nothing too majorly wrong going on right now. So, take a look back down here again. And as you can see, it's current limiting out. Now this is the voltage on the other side of the, the field coil of the speaker is in the negative lead. So I'm not really looking at the high voltage right out of the rectifier to ground. So again, the field coil is in circuit, so you're going to see that it's pretty low here. which is not too big of a deal. You can see the tubes are going to warm up, and of course the line voltage is going to move around just a little bit. Slowly climbing up again, which is kind of nice. Okay, let's verify that capacitor. Let's see what happens if I push that capacitor back into circuit. So this is our supposedly shorted capacitor here. I'll just get a bit better zoom on things here. Okay, so here I go. The lead's bent over here, so it'll touch. So here, I'll just push this in. The dim bulbs are still in, so the supply is current limited. Let's see what happens to the B plus right now. Goes down to 1.9 volts. Let that off. Back up to 82 again. That is a very, very bad capacitor. I would say it's a resistor. So, very, very bad. So, not a good thing. So, what I'm going to do now is flip this in through. And it's oscillating. If you can hear that in the speaker. I'll just move the dial around. It is in broadcast, so I'll move the dial around. Let's make sure that the volume's up. Crank the volume. Sounds like it's laughing. It's laughing at me. Yeah, it's just oscillating. So I'll move this around a bit. That's not sounding too good. Give it a bit more volume. So I would definitely say that this is not working very well. We'll just shut the supply off here. So there's an example of a radio that is in definite need of help. So I'm imagining that there might even be some open resistors because we never really checked any of the resistors. So what I'm going to do here is I'll set the radio up, and we'll go in there next and we'll just measure a couple of the resistors and see how far, if they've moved or if they're very close. And really the radio is not going to run with without it being completely rebuilt. All of these capacitors are in some state of failure. Again, very common for these older radios to do that. So we'll get in there. Really, the only cap that was doing any filtering was this. It wasn't doing too bad, with the volume down, it really wasn't humming. So if there was no filtering, to give you an idea, with no volume, the speaker would have just been really moving, would have been humming extremely bad. So that cap was taking up the slack, pretty nice. It was doing an okay job there. I imagine it's probably going to be more than 8 mics. But we'll check that out here in just a moment. So I'll just reposition the camera and we'll take a closer look at some of those other components. Let's check some of the resistors under the chassis of this Stewart Warner radio and get an idea whether we should change out all of them or maybe just 1 or 2. So just by reading the resistors and seeing how far the values have moved really gives us an idea of what kind of an environment this radio has been stored in, and whether it's been operated with really bad caps for a long time. So usually, if the resistance values have moved a whole lot, usually they've been kept in a cold garage or something with lots of temperature variation. If the radio's been kept in a house or in an attic in a controlled environment, usually the resistor values are pretty close. So, in judging by the looks of the chassis here, this looks really good, like there's no rust on the chassis at all, so I imagine it's been kept in a pretty nice environment. So the resistors are probably going to be pretty close to their value. Now, you remember the resistor code for this is body end dot, or in this case it'd be body end line, or bell, I guess you could look at it. So the majority color is the color you read first, then you go to the end, and then read the line or the dot as the multiplier. So again, blue is 6, gray is 8, and we have the number 2 here. So the multiplier, where it says 2, you can just replace that with 2 zeros. So on a resistor with a multiplier that's yellow, you'd replace yellow as 4, so you'd put 4 zeros there. Makes it a little easier to work these out. So 6800, 6800 ohms. So let's measure that resistor. And again, keep in mind that these are 20% tolerance resistors. They don't have any tolerance band on them. No tolerance band equals 20%. 6.9K, that's very close. No problems with that resistor at all. So let's read this one over here. So the majority color is yellow, so that's 4. We have purple, which is 7. And then we have the dot or the line in this case, which is orange, which is 3 zeros. So that's 4,700 ohms, or 47K if you prefer. One end of the resistor is to the chassis. The other end runs over here. No problems. It's settling off at 48. No problems whatsoever. Here's another one, 47K ohms. Let's see this one here. Get this in here. Oops. There we go. No problems. So far, just from a couple of these things, testing them, you can kind of see that this is looking like they're all very close. So changing these resistors out would really, at this point, just be the labor of love if you wanted to. So in this case, I'm going to most likely leave these in. So this one's 1 meg that I'm reading. And when you see it count like this and not really slow down, it's usually doing that because there's some form of a capacitor in line somewhere. And it's settling off just over a meg. So that's absolutely fine. So 1 meg, brown, black, and then green. Green is 5 zeros, so 1 meg ohm. So all in all, the resistors in here, I'll go through and test all of them, of course, but from what I can see here, all the resistors are very close in value, which means that it's most likely been in a very stable environment, and it really hasn't been treated all that bad throughout time. So I'm going to go through and replace all the capacitors, and I'll measure all the resistors. If there are any that are, a little bit too far off, I'll replace them, and then we'll try the thing out. If it works, we'll align it together. And through the magic of the camera, days turn into seconds. So I really did spend quite a bit of time in here. I wanted to get this to the point to where we could turn it on, see if the thing works, if not, troubleshoot it. If it does work, we can just get right into an alignment. So I'll explain some of the things that I've done here. I've added a new line cord. This is a reproduction cloth cord. They look really nice on these older radios, so I'm using that. The cable restraint or the cord restraint is 2 zap straps pulled together, and then some super glue on it just to hold it in here. So that's a real solid cord restraint here. You always want to leave some slack inside the chassis so that the cord can't pull tight on the fuse holder or on this terminal tie point. As you can see, I did add a fuse holder. Whenever I'm restoring any older radio or any older piece of gear, I always want to make sure that it's really safe. So I just add an extra little piece of protection in there and put a fuse holder in. Now I haven't selected the value of the fuse yet. I've just put a 1 amp slow blow fuse in here for testing purposes. In the end, I will determine the value of the fuse that should be in there. So it is pretty much ready to test, and it should be interesting to see if this thing works. Pretty much what I've done is I've just recapped the whole thing, and there was a bunch of resistors that were kind of on the border. So I changed out 3 resistors, and I hopefully you can see these in the camera here. So there's one here that I changed out. It's a 100K ohm resistor here. There's one here that I've changed out. This is a metal film resistor, and there's another one right here, which is a 22K resistor. And those are the only 3 that I really had to change. All the rest of them are very close. So you can see all the new caps, all the yellow caps. The new filters are down in here. So there's 1 filter here and 1 filter here. So it's nicely tucked out of the way. They're nice and small so they can fit right into the chassis. And there's 1 filter right up here. So close to where the old one was up here. I've cleaned all the switches. I've sprayed contact cleaner in here and I've cycled them. How I did that is I basically held 1 button down. So we'll say this one here, held this one down, and that pretty much disables the latching mechanism if you keep your finger on it like this. And then, so say I was going to cycle this one here. So what I would do is I would just push this down like so, and you can see that, well, if I can get my hand in here properly, like this. You can pretty much cycle the switches just like this, and then you go to the next one. And that allows you to spray contact cleaner in there, and you can cycle them very quickly, and you do that a whole bunch of times. And then, of course, a lot of the contact cleaner is going to run down into the bottom of the chassis here, so clean that all up and then hose it down again and cycle it again like that. This is done with obviously no power to the radio because we haven't powered this up, right? So you want to do this with no power in the radio and just cycle them a whole bunch of times and just get rid of the oxidization on the contacts in the switch. It's the whole switch mechanism, and usually, it's pretty foolproof. They usually work fine after you hose them down with a decent contact cleaner. So yet to discover, I'm imagining one is going to be the oscillator and one is going to be the antenna. These are the tuning capacitors for each switch on here. So we have 4 active switches. We have this one, this one, this one, and this one. So this one here is the phonograph switch. This is shortwave and broadcast. So we have 4 presets. So, we have 4 sets, right? 1, 2, 3, and 4. So one of these is going to be the oscillator and one is going to be the antenna. You'll notice that on the top of the chassis, there's a dual gang tuning condenser on the top. So in order to properly tune in the station, one will tune the oscillator and then one will peak up the RF, make it more sensitive. So basically peak the antenna circuit. So it'll be, one of these will be it. And we'll discover that here in just a bit when we apply power to it. Let's see, what else can I tell you? I haven't really cleaned the top of the chassis yet. I haven't dedusted any of the tubes or anything. I've just, spent all the time in here, and this is to the point to where I am now. As you can see, I really haven't cleaned off the top of the chassis. You can see all the dust is still on the transformer here. Any of the dust that's missing is just from me handling this thing, moving it around to change the caps and things like that. And I haven't even looked at any of the tubes or anything. Oh yeah, we were going to look at the tube shields here and see if they are goat shields. They look like they probably are. Let's see if I can get past here. So what I'm doing is I'm just putting a bit of pressure on the cap as I'm removing the connection here because I don't want to pull the cap off the tube. A lot of these tubes, it's 1940, right? So these caps sometimes get loose on the top of the tube, so it's always nice to put a bit of down pressure as you're pulling up so that you don't remove the cap off the tube, then you're left with a dud for a tube. I'm hoping that these all work. So there it is, goat. If you can see that in there, I'm hoping you can. So goat shield. Basically all you do is just remove this retainer ring here. So pull that retainer ring off, pop it down here. Kind of doing this around the camera here. And they just come apart in 2 pieces. And since I've got this apart right now, what I'll do is I'll just leave this off and clean the tube off. 6Q7 looks like it's in nice condition. Westinghouse tube, Westinghouse tube. So I'm wondering if these are the original tubes. So I'll take all the tubes out and clean it off and dust off the top of the chassis here. And then what I'll do is I'll get the speaker. I also fixed the crack in the speaker as well. So I used a bit of glue on that and glued that, and the cone still moves. There's no binding or anything on the voice coil, so I'm imagining it's going to probably work okay. So I'll get all this stuff done, and pretty much to the point to where we're ready to plug it in and try it out. We're pretty much ready at that point right now. What I'll do is just clean this all up and get this ready for the alignment. I don't want to do the alignment and then go back in here and start pulling tubes out to clean things up, because sometimes that messes with the alignment, especially the RF or the oscillator portion of the alignment, I should say. So once you do the actual dial alignment on the front to make sure that the dial lines up with the frequency that you're receiving, you really don't want to be pulling any tubes or moving anything around after that point, because there's a chance that you're going to throw your alignment out. So I'll get all the cleaning done here and I'll be right back. All right, let's see if the Stewart Warner comes to life. So what do you think? Do you think we're going to have to troubleshoot this, or do you think it's just going to come right to life? Well, let's find out. So I have the speaker hooked up, and it's pretty much ready to go. I just have to plug it in and hook up the antenna. I guess I could have probably hooked up the antenna off camera. So I'll just do that right now. All right, get that out of the way, and I'll plug this into the variac. So the variac is just turned up. And I've got it on through, so there's no current limiting, so we'll just turn this on and see what happens. All right, so here we go. I guess we're going to need to have it on broadcast, so it'll receive something. Turn the volume up a bit, and we'll see what happens. And it's coming to life right away. The capacitor is fully meshed, too, so it's right at the end.
Buenas nastiest to you.
Jess, you say you were lucky.
Blue line towards that line.
Radio has state position, having won all those.
Point range 50%.
Wow. No alignment or anything, just caps and a few resistors. Look at that. So let's try shortwave. See what happens with that. Turn this up. And that's receiving. Whether there's anything on the bands is to be discovered.
Beholding her and acknowledging.
Wow. Got lots of volume too. There's quite a bit there. So lots of volume. So it's looking like the tubes are nice and strong and everything. So we're pretty much ready to do an alignment at this point. Everything is working really good. Let's test some of the push button switches here. So I'll turn that down and maybe give it just a bit of volume. Let's see what happens. I don't know if any of these are programmed or anything, right? So sounds like it's off frequency, but it's there.
Some days.
So they probably need to get programmed. And that's just adjusting those capacitors on the bottom side of the chassis. Not bad. So if I push the phono in and I touch that phono input on the back, it should probably make a buzzing or humming noise. Yeah, no problems. So it's all there. Wow, very impressive. No alignment or anything. So obviously this thing hasn't been screwdrivered too bad over time. Or if it has, it's been screwdrivered back. Not bad. So let's get into the alignment and really make this thing perform. I'm ready to perform the IF alignment on this Stewart Warner receiver. The IF frequency of this receiver is 456 kilocycles, or kilohertz if you prefer. I'm going to be using a vacuum tube voltmeter and an RF signal generator to perform this alignment. The vacuum tube voltmeter is across the voice coil of the speaker. So I've modified this just a little bit because this is on camera and the tone gets pretty loud. So I've desoldered one of the audio output transformer's leads and I've put a 100 ohm resistor in series with a voice coil just to knock the tone down a little bit. So normally you would just put the VTVM right across the voice coil to perform this alignment. These are the alignment points right here on the receiver. So these are the IF transformers and we have 4 points to align. Up here is the signal generator. So it's set to 456 kilocycles. And as you can see over here, it's about 300 microvolts output and it's modulated to 50%. So there's a tone on that right now. That tone is what we're going to be using to align this right here. So the first thing that they want us to do is make sure that this dial pointer is fully aligned. So that's the very first thing. So they want you to mesh the capacitor fully. So bring the capacitor to the lowest end of the dial. So that would be 550 kilohertz. And then make this fully horizontal. So fully meshed means that you can't turn the capacitor anymore. It's fully meshed. It's fully in. And put the dial pointer fully horizontal. Very first thing to do. And that's listed right here in the alignment procedure right here. So what they want us to do first thing in order to do this IF alignment is put a 0.1 microfarad capacitor across the antenna terminals. And that's what we've done. So basically we're just making the receiver deaf by doing that. That's all we're doing. So that's the dummy antenna, 0.1 microfarad condenser. It says here, connection of the signal generator to receiver stator terminal on top of the rear gang section. So this is where we're feeding the signal in from the signal generator. I've got this capacitor here in line with my signal generator just to act as a DC block if something was to ever happen, that's all. So this is where we're tied in. So this is actually the portion of the capacitor that tunes the antenna. And these track with the oscillator. So this one up here is the oscillator in the front. This capacitor tunes the oscillator, and this tunes the antenna section. And because they're ganged together, they track with one another as you're moving the dial around. So that way everything is peaked all the time, so it keeps the antenna in tune with where you're tuning the dial. So dual gang capacitor here. So this is where the signals fit in. So in order to start this alignment, what I'm going to do is turn up the volume. And you'll hear the tone in there right now. So if we look at the vacuum tube voltmeter here, you can see I have just a little bit of deflection of the needle there. So now what I'm going to do is I'm going to tune this one right here first. So I'll stick my insulated screwdriver in there, and I'm going to tune that. So here we go. Wow, that's really detuned. So you just go back and forth until you get a maximum signal. So now what I'm going to do is turn the volume down. And I'm also going to turn my signal generator down just a little bit as well. Okay, and I'll turn the volume just a little bit. So that's at full volume now. So now what I'm going to do is go to the next one. So I'll go to this one here, and then I'll work my way over to these two over here. So now I'm going to adjust the next one here. Wow, this is way out of adjustment. Have to turn the volume down. Wow. So you just go back and forth until you get a peak reading. That little bit of that crackling that you hear and the needle jumping is just this little metal end on the tool right here touching that screw. That's what's making that kind of a crackly noise. So now what I'm going to do, just turn this down a bit, is I'm going to go to the next transformer here. So now I'll adjust these two right here. I'm also going to turn down the signal generator just a little bit more. If I can get around here. So now I'm down at 60 microvolts. Turn the volume up just a little bit. Now I'm going to make those adjustments on the IF transformer right now. Incredibly out of adjustment. And it was receiving so well too. Boy, this is going to really be receiving when we're done with this. So you just got to go back and forth until you get it up to its max. And that's the other one. Wow. So far out of adjustment. So I'll turn the volume down here a little bit. Okay, so now what I'm going to do is just repeat the whole procedure again. So now that it's pretty much peaked up, so now what I'm going to do is I'm just going to start here and go over these one more time. So I'll start with the first one here, just to make sure that everything is peaked up. That's just good practice. So I'll turn this down just a little bit, like so. And I'll also turn the signal generator down just a little bit. Turn the volume up. So now I'm at 30 microvolts out. So here we go. I'll make the adjustments on the transformer here again. Now I'm on to the other transformer, the last two. And that's it. That pretty much performs, or is the entire IF alignment procedure. Pretty easy on a receiver like this. So all of these have now been adjusted. So it's been peaked up at 456. I'll just turn this down. It's been peaked up at 456 kilocycles. So that IF was way out of adjustment too. And it was receiving so well. So this receiver is going to do really good once we perform the RF alignment. And that will be next. Before we get into the oscillator and RF alignment, we need to adjust the wave trap first, and that's that little adjustment right there. Basically, the wave trap is just a notch filter at 456 kilocycles. So what we do is we attach a standard RMA dummy across the antenna leads. So in this case, I have this little box that I use. It's a little bit more flat than an RMA dummy, but I'll show you guys how to build one of these in the near future here. But for this alignment, an RMA dummy is just fine. So my signal generator is fed into this, and this is just attached to the antenna leads. So what we need to do is turn the signal generator up a little bit. I've got mine set to 200 microvolts now. And we want to tune this until we get minimum signal, because this is a notch filter, so we want to notch that out of there. So we'll take a look at the VTVM again. I'll turn up the volume, and you can hear that in there. So now what I'm going to do is just tune this for minimum signal. See, now I passed it, so I need to back up. So I'll just turn this up a little bit. Make sure I've got this at the lowest point. That's about as low as it gets. So I'll just show you exactly what I've done here with the control. You can hear the difference. I'll just turn up the volume a little bit. It's getting loud now, so I'm out of the notch. See, I passed it. And that's about the minimum right there. And that's how you adjust the wave trap. The next thing we're going to do is adjust the dial tracking. So, for example, if the needle is pointing at 1500 kilocycles, we want to be receiving at 1500 kilocycles. So if this is out of adjustment, it might be pointing at 1500, but we might actually be listening to, say, 1300 or something like that. So it's very important to get this as accurate as possible. And the steps to do that are as follows. So it says here, standard dummy, so same thing that we had hooked up before, to the antenna leads. We have to tune our signal generator to 1500 kcs or 1.5 megacycles, whatever you want to call it. The receiver dial setting has to be at 1500 as well. So I already have the signal generator here, so what we'll do is we'll tune the dial to 1500. Now it's a good idea to look at the dial square on when you're doing this. So I'll just get this right up to 1500 here. Turn the volume down. And I'll just make sure that it's pointing exactly there. So that's 1500 right there. So now, in order to make that adjustment, we have to adjust oscillator shunt C6. So if we look here, oscillator shunt C6 is on the back side of the chassis, and We need to turn the chassis around so that we can get to that. So we want to tune that capacitor until we hear a tone. So just move the chassis around. So there it is. That's that center hole right there. So turn the volume up just a little bit. See how it's trying to receive radio stations? It's hooked up to a dummy and to a signal generator, and it's still pulling in radio stations. This thing is going to be a pretty sensitive receiver. All right, so I'll adjust this now until I hear a tone. There it is. So there it is. So now that's aligned. So when it's pointing to 1500, it's receiving 1500. So I'll just turn the volume down. So I'll move this around here. Now the next step is, let's move the light out of the way. So the next step is to adjust the antenna shunt C5. So everything's still hooked up the same. So we want to adjust this for maximum sensitivity. So we're adjusting this till you basically have the receiver as sensitive as we can get it. And here it says adjust for maximum output. So that right there is C5 right down at the bottom. You can see that. C5, bottom it says. I'll turn this up. And I will adjust this for maximum sensitivity. And it's pretty much there already. So that's adjusted. So next, it says here, same thing, standard dummy, antenna lead. Now we need to tune the signal generator to 600 kilocycles and tune the receiver to 600 kilocycles. So I'll tune the receiver there first. Again, it's a good idea to look at the square on when you're doing this so that you get it pointing exactly at 600. There it is, 600. So now, turn up the volume. And I'll move the signal generator to 600. 600 kilohertz. Wow, and it's there. So it doesn't even sound like we need to adjust that. And that would be oscillator C8, and that's right here. So that would be the one closest to the transformer on the back side of the chassis. So I'll move this around. Just like so. Closest to the transformer, that's this one here. And right there is its loudest point. So now you need to repeat this again. So now we're going to go back up to 1500, check it again, make sure that it's spot on. If not, we'll touch it up, and then we'll come back down here and do this procedure again. And that's how you have to do this. You have to go back and forth until the dial is perfect at each end. So to give you an idea, let's just go back up to 1500 here and see if it's on. Usually when you adjust one, it affects the other just a little bit. So move this out of the way here. So I'll go to 1.5 megahertz. So now I got to roll the dial back up here again and see if it's moved off. And it's perfect. So we don't need to go through that adjustment again. No problems. So that's the procedure. You go back and forth and test them both. You can't just adjust 1500, go to 600, and then forget about it. Once you've adjusted the 6, sometimes it pulls this end down. So then you need to adjust the top back up, and you need to go down here. So it's almost like you're stretching it out, and then you can shrink it up as well using those capacitors. So this just happened to work out very well, and I have a feeling the reason it worked out so easy this time is because 600 was pretty much aligned already. It was right there. So that was a nice easy alignment. So the next alignment will be, it says on the paper here, it says here 1500, C5, C6, and C5. Yeah, it's just telling us to do it over again. And then, so the next one is just the short wave band. And after that, we can check out making some of these, well, the magic keyboard, it's called, making the magic keyboard work properly. The next portion of the alignment is the short wave band. So it tells us that we need to get rid of our RMA dummy and use a 400 ohm carbon resistor instead. So that would be across those two leads. So if you're using an RMA dummy, you would want to change that. I'm not using the RMA dummy. I'm using this box over here, so I can just leave that in line and not worry about changing anything. So now we have to tune the signal generator to 15 megacycles, or 15,000 kcs. And we also have to tune the radio to that as well. So we want to put it onto the short wave band. And again, we need to adjust this, so you want to look at this square on. And it's right about there. So it says we have to adjust the oscillator shunt C7, which is this one right here. It's closest to the IF transformer. And so what I'll do is I'll give this a bit of volume. And instead of moving the radio, I think I'll just do this instead. There it is. Very touchy adjustment. So now it tells us, let's turn that down. So now it tells us to adjust the antenna shunt C4. So now we're just peaking up the RF, really, is what we're doing. So it's going to make it more sensitive. And C4 is at the top. So this is the next adjustment. As you can see, it says adjust for maximum output while rocking the gang. So you can rock this back and forth and peak for maximum output. So we're going to be adjusting this one right here. So I'll turn this up. And that's at its peak right there. And that concludes the short wave alignment. That one's nice and simple. So move this around. Here it's still trying to receive signals. That's hearing my 10 megahertz reference right now, so that's doing pretty good. Nice and sensitive. Again, no antenna. Just hooked up to the RMA dummy right now. Right over there. So, pretty sensitive receiver. This is going to be a lot of fun to hook this up to an actual antenna here in just a little bit and see how it really receives. Alright, let's adjust the magic keyboard. So here we go. press this button in. So these two will be for this button, these two will be for this button, and so on and so forth as we go down. So let's try this. So this is adjusting the oscillator. So this will be oscillator and antenna. So that's how it's going to go. So now what we need to do is peak it. You can see that it brings the signal down, so we're tuning the antenna section now. So that's that one. So if we go down to the next one, we'll find another radio station here. Something that's not going to... So now... So there we go. So now, if I go back to this one, well, this one here is programmed, or somewhat programmed. So there it is.
I got confidence in myself. I can possibly be in. If I make it, it's great.
So there it is. That's how the magic keyboard gets tuned. So oscillator antenna for each one of the buttons. It's pretty easy. Let's take a listen to the old Stewart Warner and see how it performs. So here we go.
Need to be affirmed and still needing direction.
Oh, absolutely. Fatherless.
In the grass, in this meadow. When I was coming up,
we got drips and race and local talent. In radio, I've seen it in the trade publication.
And race-based immigration system.
Time, not Chuck, no. They mouth off during the weekend. It works okay.
600.
But the bride is looking...
Documents and where can the policies go?
By Wednesday, to be forgotten and something could...
if you need to,
I think... I believe as I think you believe.
but stories, I do have some more, actually.
Are switching to...
Did money switch to Geico? On car insurance. Up next.
He could have gone.
Okay. I don't think she's devoted.
Well, it's working extremely well. Very sensitive receiver. Should be fun to listen to some late night DX with this. Let's check out the Stewart Warner's performance on short wave. So I'm not sure how active the bands are right now, but we'll take a listen at any rate. You can really hear it's trying to receive hard. Just don't think there's anything down here right now. Something there. Keep in mind that different portions of the band come active at different times of the day. So it really just depends on the conditions. This usually is a later in the evening portion, right in here. So then right now it's about midday. We'll probably start hearing some stuff here soon. So that's some side band. This is an amateur band. Types of stations mixing.
You gonna tell me?
That's the time signal at 10 megacycles.
Estoy tratando de dar el mejor ejemplo y animando a la fe de los hermanos.
En un contexto global convulso con...
This is another ham radio band here, just about 14 megacycles. Lots of CW in there. That's a really strong time signal there. That's at 15 megs. It was overloading the receive. It's so strong, actually. So this is a single conversion super heterodyne receiver. And usually when you get this high in frequency in a single conversion unit like this, especially pretty much in, just a 5-tube radio, you do get image frequencies. So usually you'll hear the time signal at two separate areas really close to one another. So the one at 10 is correct, it's at 10. And then this one here is at 15 megacycles, but you're going to hear a time signal around this, especially when it's that strong, because it's just overloading the receiver, right? The conditions are really good up here. So, like that's a really strong signal. And I think that's about it for the bands. So lots of activity down in here right now. Later on at night, this here will come to life, this little portion right here. Again, it's just really dependent on the time of day. So it's a great little receiver. It works really good. You know, and if you're interested in shortwave listening, because you can see the bands are really quite active still. And again, you know, it all depends on the time of day where you want to really listen here. So lots of activity in here. Let's go down here one more time and see if there's anything else coming in. There is something there. So yeah, I'll just have to wait till later in the evening to receive stuff down in here, but you get the idea at any rate. So it's a great little receiver. So what I'll do now is I'll probably spend a little bit more time on the cabinet and try and clean it up, maybe settle off some of this. This here is like, I kind of look at this kind of like patina in the cabinet itself, and you know, I don't really know if I want to get rid of that. It really just depends on the light that it's in. It does show up in some light better than others, and it really doesn't look all that incredibly bad. It almost look like little hairline scratches. So all in all, I'm very impressed with this little radio. For basically a standard 5-tube radio, this is really working well. It's just got gobs of receive on the standard broadcast band, and it's really strong on the shortwave bands as well. So Stewart Warner did their homework. It really works well, and you'll notice that as I move this through the shortwave bands, that the static is pretty consistent all the way through, so there really isn't all that many dead spots in the RF tuning of this particular receiver. So that means that they did their homework. They did, they spent the time and tried to make this perform as, as good as they can for 5 tubes. And I think they did a wonderful job. So I'm going to have a lot of fun listening to broadcast band DX and listening to the shortwave band on this. I might even have this thing playing in the background as I, work here at the bench, things like that. Really does have nice sound. The speaker itself is not distorting in any way. It's not buzzing or rattling. So that little fix to the crack in there worked really quite well. So all in all, I'm very happy with this little radio. I really think it's, doing its job. So just a bunch of capacitors, a few resistors, and a bit of tuning, and look at that. The thing really is quite a conversation piece. If you turn this thing on when company comes over, it's definitely going to attract attention, especially with this really nice looking gold dial. They really did a nice job on that. When the lights are out and the light just shines on this, it really does light up gold. Really looks really nice here. See if I can get rid of some of the lights. There you go. You can see how nicely that lights up. So, very nice looking radio. All in all, I would say, this Stewart Warner works well. I'm very impressed by its performance. So, on to the next project now. Thanks for stopping by the lab today. Hope you enjoyed this episode involving this really neat old Stewart Warner radio. If you did enjoy this video, you can let me know by giving me a big thumbs up and hang around. There'll be many more episodes coming like this in the near future. In fact, the Old Time Workbench is just about complete. So very soon, together, we're going to be selecting older test gear from that shelving in that room. We're going to repair and restore that older test gear, populate that workbench together. Then we're going to start repairing antique and modern equipment with that very old test gear. I'll show you all the tricks to do that. So it should be a lot of fun, so definitely hang around. If you're interested in learning things about electronics that you just won't learn anywhere else, you might want to check out my ongoing electronics course on Patreon. I'll have the link just below this video in the description. If you click on that link, it'll take you right there. When you do go there, check out the community section. There's many people sharing their projects and ideas there as well. All right, thanks for stopping by. I'll see you very soon. Bye for now.